Hello everybody, welcome to section 3.4. Today we're going to go ahead and continue working with the chain rule. We're also going to mix in product rule and quotient rule. So we're going to do chain with product or product with chain, kind of mix the rules together to find our derivatives. So let's just go ahead and recall what is the chain rule, okay? So we use the chain rule when you have a function inside of a function, okay? So in this case, I have g of x inside function f of x. In order to take the derivative of a composition of functions, you take the derivative of your outside, okay? Put your original inside back in, so plug that in, and then you multiply it by the derivative of the inside, okay? That is how the chain rule works. So let's go ahead and look at our first example. It's a little bit more complicated because I have this first function being multiplied by the second function. In order to do this, it's really a product rule with the chain rule. So we got product with chain. And one thing I would actually notice is I have to do chain not once, but twice. Okay. So I'm mixing the two rules together. So let's start this out by just saying what is the inside and what is the outside of each part. So if I just focus on this first function, this would be my inside. Okay. And then the 5 would be the outside. X to the 5th would be our outside. If I look at my next function, the inside is right here, and then the outside would be the x to the 4th. But our overall rule is product, okay? So how do we do product rule? We have product as our first function times the derivative of our second function. So in order to take the derivative of my second function, it's a chain rule. So I go ahead and multiply it by the derivative of my outside, 4, with the original inside, to the 3rd. Okay, so times the derivative of the inside. Derivative of my inside would be 3x squared minus 1. All right, so it's looking like we got quite a bit going on, but we're following through with our product rule. So we got first times the derivative of our second. So this is all the derivative of our second. Plus our second function. So I'm going to rewrite the second function. Times the derivative of our first. Well, in order to take the derivative of the first, it's a chain rule again. So I bring my 5 down in front, so it's 5 with 2x plus 1 to the 4th power times the derivative of my inside. Okay, it's 2x plus 1, so just 2. So here is my derivative all written out. My product rule with my chain rule mixed in there. Okay, so now I'm going to simplify. This is to the 5th power, so it's going to stay as is. And this is to the 3rd power, and that's going to stay as is as well. Okay. If I wanted to simplify it, I have to write it 5 times and FOIL it out. If I wanted to simplify this piece, I'd have to write it 3 times and FOIL it out. Okay. However, this one is to the 1st power, so I can actually distribute that 4 to that parenthesis here. So I'm going to do that. So y prime equals, distributing my 4 to this parenthesis, I would have 12x squared minus 4. And now I'm just going to rewrite the other two parts that I have. I have 2x plus 1 to the 5th times x cubed minus x plus 1 to the 3rd. Plus, now I'm going to simplify this next part. These two pieces again, I can't do anything with them unless I write them 4 times and then FOIL it all out. So I would just say 5 times 2, I would have 10, and then I'm going to rewrite those other two pieces. So I would have x cubed minus x plus 1 to the 4th times 2x plus 1 to the 4th. Now from here, this is a good answer. However, if you were to check your answer with the back of the book, it would actually be simplified a little bit more. So here is my first part, and got a little crowded, but here's my second part. Do they have any greatest common factor? Or is there anything I can take out of both parts? This one has x plus 1 to the 5th. Do you guys see how this one has x plus 1 to the 4th? So I can factor out an x plus 1 to the 4th. It's like if I had 2x to the 5th plus 3x to the 4th. The GCF would be x to the 4th, so I could factor that out. So I'm going to do that now. I can take out an x to the 4th. So I would have 2x plus 1 to the 4th. Is there any other GCFs like that? Is there any other terms that look just like 12x squared minus 4? I don't see that here. How about x cubed minus x plus 1 to the third? X cubed minus x plus 1 to the fourth. So I can take out an x cubed minus x plus 1 to the third power. And now from here, I'm going to write what I have left. So this part is going to stay. So I would have 12x squared minus 4. I have factored out 4 2x plus 1s. So now I will just have 1 left. So 2x plus 1. And then here, I have actually factored out by GCF all 3, okay, to the third power. So that I don't write anymore. Plus, I still have my 10. And here, I factored out x cubed minus x plus 1 to the third. And I currently have it to the fourth power, so I will still have 1 of those left. And then this last part, I have factored out all of it. Okay, so we are done here. Then the last thing I would need to do is simplify what I have here in my bracket. So I have 2x plus 1 to the fourth. I have x cubed minus x plus 1 to the third. And then I would FOIL this out. Okay, so I have 12x squared times 2x. So I have 24x cubed plus 12x squared. Distribute my negative 4, so minus 8x minus 4 plus, and I'm going to distribute my 10. So I would have 10x cubed minus 10x plus 10. And now from here, I just need to combine my like terms. So y prime equals, this first part stays the same, x cubed minus x plus 1 to the third, and then I would combine my like terms. So I would have 34x to the third plus 12x squared. Put those two together, minus 18x. And then I have negative 4, and this was 10, so plus 6. And that would be my final answer for example 1.